Good morning, everybody, or afternoon or night, depending on which time zone you are in. My name is Anton Feenstra. I'm from the Free University in Amsterdam, and I'm very happy to be able to present our work here this year at 3DSig. And we've been working on the sequence-based prediction of conformational epitopes. So these are B-cell epitopes, and as you might know, they're the antibody binding region of antigen proteins. This recognition is very specific and used extensively, for example, as diagnostic tools or therapeutics, and also in the development of vaccines. However, the development of antibodies that are routinely used is often proprietary. The methods aren't always open, and it's therefore very hard to optimize antibodies for good efficiency. Also, if you are facing a new pathogen, an emerging virus, you might not yet have a structure available to do your analysis on, and then the sequence-based predictor might be the first thing that you could use as soon as new genomic sequences become available. So, zooming out a little bit, epitopes are in a way just a type of protein-protein interactions. Just as a quick summary, there are heteromeric and homomeric interactions. So when two of the same protein bind, it's a homomeric. And if one protein binds a different protein, it's heteromeric. And if one of them is an antibody, then we call the binding region an epitope region. We've previously developed a random forest method to predict heteromeric and homomeric protein-protein interactions, generic PPIs. And we are now presenting the work of how we apply the same approach to predicting the antibody binding site, so the epitope region of the antigen protein. So to train a good classifier, there are two main things you need. You need features and you need good data sets. So as features, we've used the same ones we've used before. So that's conservation, solvent accessibility, and the secondary structure, which we predict from sequence using the tool NetSurfP. Then we predict from sequence background dynamics using tool Dynamine from the group of Pim Franken, and we added protein length. And then we use a 9-residue sequence window. So to predict the central residue, we use the features of the 4 flanking residues on either side in the sequence. Now, as a data set, the main data set is derived from the SubDub database built in the group of Charlotte Dean in Oxford, and from that we derived a set of 280 antigen proteins, and we've mainly filtered down on sequence identity up to a maximum of 25% to remove redundancy and biases of well-reported and well-studied proteins. And then in addition, we're also reusing a data set of homomeric interactions and heteromeric interactions that we've used before. So one of the things that we also do, and many people do this, is that we encode evolutionary information. And so starting from the query sequence, we use SciBlast with the lenient e-value cutoff to find homolog sequences, which we align using muscle. And then we calculate the feature for the query sequence, but also we calculate the features for all the homolog proteins in the alignment. And then we take the average and the standard deviation of each feature value at each position. And so there's 6 features with 3 values each. And then we have the entropy, which is calculated once for each alignment column. And then we have the 9 residues sequence window and protein length, which add up to 172 features that we use as input for the random forest model. Now, the first thing we tried is just take our previously trained generic serendip PPI protein classifiers, and we had 3 flavors, one trained on heteromeric interactions, one trained on homomeric interactions, and one combined. And here we've tested them on the antibody test set. There are a lot of numbers here. You can focus on the last column, the area under the curve of the rock plot, where you can clearly see that the heteromeric trained generic PPI predictor is best able to identify the epitope regions. But the epitopes might actually be slightly different than generic protein-protein interactions. So here I've copied the heteromeric predictor, and then we have 2 new predictors, one trained on only the antibody data set and one trained on the combination of the heteromeric proteins and the antibody data set. And now you can see that the antibody trained data predictor already does better, but the combined trained one does best. The antibody trained predictor is probably slightly more specific, and then this one is slightly more generic, and it can take the advantage of training on more data, even though not all the data is actually epitope data. So that's the main result actually for today, but we can dive a little bit deeper. And the first thing we want to see is how does this compare to other methods that are available. There are 4 that we have used, that we could use, and that's Bepipred version 1 and 2, Epipred, and CBTOPE. This is the rock plot from which I showed the areas under the curve before. And you can clearly see that both serendip methods, so the antibody trained and the heteromeric plus antibody trained one, are clearly much higher in the rock plot than any of the other methods. These are all tested on the same antibody test set that we've used before in the table. And all of these are sequence-based methods, so they only take sequence as input and they don't use any structural data. We can take the precision recall plot, which basically zooms in onto the most highly scoring sites for each of these prediction methods. And then you can see that with the antibody trained method, we can get the highest precision. Most of the other methods actually also get a high precision at the start, but then they drop off quite quickly. And then we can see that the heteromeric and antibody trained method actually peaks later, but overall retains a higher precision even at at higher recall. This plot is cut at a recall of 10%, but this trend actually persists. In both of these analyses, you can see that our new serendip CE conformational epitope predictor works quite well compared to other methods, at least tested on our dataset. So the features are the most important thing in the predictor that make it work. So which features are actually at work here? We've used all 172 features. There's no feature selection needed for random forest models in general. I show here a heat map of the feature importance measured by Gini impurity for 5 different models. So the antibody trained, the hetero and antibody trained, and then the 3 old models, heteromeric, combined, and the homomeric. And then the top features, this 172 features. Top features are always the same for all of these models. That's sequence length, and I'll come back to that in the next slide, and solvent accessibility. And that's just the solvent accessibility for the central window position, and the other window positions are a little bit lower in the ranking. The ranking, by the way, is done by the feature importance of the antibody-specific trained random forest model. Now then we see a block of entropy that measures conservation, and you can see there's a red block here, which basically says that this is more important for epitope binding than for the other models. And if we look at the two leftmost columns, which are partly trained on homomeric interactions, we see that it's much less important there. And then we have a couple of blue stripes across the heat map, which correspond to the propensity for coil predicted by NetSurf P. And this means that this propensity for coil is much less important for the prediction of generic protein interactions, and it's relatively more important for the antibody predictions. To confirm this, because the Gini impurity doesn't always measure everything you want to know about how important the feature is, we have also retrained models with some features removed. So when we remove just length, which is a single feature out of 172, our AUC ROC, just look at the AUC ROC, drops from 0.69 to 0.63. That's quite a significant decrease. If you actually train a model only on the solvent accessibility features, we get a similar performance actually than when we just remove length. If we remove solvent accessibility, so we turn it around and we train on everything except solvent accessibility, then we're getting performance that's a little bit lower, but still quite close to the model with all features included. And then, of course, if we remove both of them, the length and the solvent accessibility, then our model drops down to, well, a little bit, but not a lot above random. 0.5 in a rock plot is random. So length is the most important single feature by far. It's position independent in the protein because, of course, length is the same for all positions in the protein. And we think this the reason that it's the most important feature is simply because it tells the model what size protein you have. And there's two effects there. One is that a bigger protein has less surface, and obviously your epitope will have to be on the surface, but also, relatively speaking, the variation in size of epitope regions is limited. So a big protein will, in relation to the size of the protein, have a relatively small epitope region. The other way around as well, small proteins will have relatively large surface area compared to the number of buried residues, and also a relatively large epitope region. So this allows the model to normalize on these effects effectively. So the solvent accessibility is not a single feature, it is actually 54 different features. Now, since this is 3D-seq, you would also like to know, does structural information actually help? And I've taken here are both models. And here I'm comparing this with a couple of structure-based epitope prediction models. These are the best ones I could find in literature. This is our antibody trained model, and this is our combined heteromeric and antibody trained model. These values are the same as what you saw before. Then I've looked at Discotope, Pecan, and PINet as benchmarked by Day and Bailey Kellogg this year. And then we can make a nice comparison, and you can see that PINet, their epitope trained PINet, does very well in sensitivity, a bit less in precision. And then Discotope does very well in precision and a bit less in sensitivity. Now, the previous talk, at least if the program hasn't changed between now and the conference, was on Epitope 3D. And from their website, I could find that their F1 score is 0.36, which is quite a bit better than our F1 score. But unfortunately, these tests were done on different data sets. So the benchmark, this recent benchmark is a different data set, and then the Epitope 3D, I'm sure, was also tested on a different data set. So the difference, I must say, between the sequence-based and the structure-based methods here is not as big as it might have been. So either there's still a lot of performance to be gained in the structure-based methods, or maybe epitope regions are relatively easy to predict from sequence. I think this is still open for discussion. Then, this is the year of COVID, so I'm showing you here our predictions for the SARS-CoV-2 receptor binding domain, where on the left side you see the crystal structure, and the red areas are the parts that are in contact with the antibody in the crystal structure. The antibody is not shown in this figure. And on the right side, it's the same protein with our predictions color-coded. The red ones are the highest scoring sites, so most highly predicted to be epitope, and the blue is the lowest score. And you can quite clearly see that the overlap is quite high between those sites. The alignment at the bottom actually shows the same information, where you can see a little bit more detail. If you plot this in a rock plot, you get an area under the curve of almost 0.8. And at a recall of 12, we get a very high precision of 56. If you're interested, I can show you the full rock plot of this prediction later. So in conclusion, the main points are that we have a prediction method that works from sequence. We've used evolutionary context in an alignment. We also have a web server that you can use, and you simply have to input your sequence. It includes the generic PPI predictor models and the epitope predictor model, so be sure to select the right random forest model. for the prediction you're interested in. Our method is better than the methods that we've tested that are based on sequence, at least on the data set that we have tested them on. And it's not too far below structure-based methods. But of course, if you have an experimental or predicted structure for your protein of interest, then there are also a lot of other analysis that you might be able to do based on that. So with that, I've come to the end. I'd like to thank you for your attention. I'd also like to thank all of my co-authors, and in particular, Henriette Kapel, who started this project as her bachelor thesis, and Qingzhen Hao, who picked this up and made it into the first draft of the manuscript. I'd like to thank the Free University and the Myriade European ITN project for financial support. And with that, I'd like to open the paper for questions, which will be online.